Hello again, folks. So, what we have here is a video about bonding and Lewis structures. Now, we're going to start here by doing the basic intro about what it takes up to make some bonds, and then I'll actually jump ahead to the non-intuitive structures, ones that do not follow a lot of rules. In fact, you have to kind of take a kind of a artistic hand. You have to follow some basic premises, but if you can think your way through these guys, organic structures are far easier in the long run. Let's go ahead and get started on this. So, this chapter is all about bonding. And so, we'll start with ionic bonding. This will not be a large focus of this chapter, so we'll get it out of the way early. But remember, we talked about earlier about our valence electrons, about how we have the s and the p orbitals, and how they tend to like to be either filled or emptied. Well, when we have metals and nonmetals, our bonds are formed through electron transfer to form our cation and anion pair. Remember, they're going to try to achieve this by emptying out s and p orbitals, if at all possible. To be like a noble gas, have a filled core set of electrons or a filled valence set of electrons. Either want to have zero valence or full valence at best. So now these pairs are, as I said, held by electrostatic attractions. Basically, opposite charges attract. So if you have a positive charge and negative charge, they want to stick together. So we can imagine we're drawing a sodium with its one valence electron. It loses it to become sodium plus 1. We have chlorine with its 7 valence electrons, gains an electron to become 8 and minus 1. And this positive and this negative are naturally going to attract. The same can be true for aluminum with its 3 valence electrons. We ionize each one and give 1 electron to 3 different chloride ions. And these 3 different chloride ions can then be attracted and bonded to the aluminum, thus giving it electrons back and stabilizing it. So note how they either want to empty out all of the valence electrons in the case of sodium and aluminum, or completely fill out the outer set to give it an octet. Well, remember, our ionic bonds are not just a single pair of ions, but rather a million trillion ions. And it's going to generate a crystal structure like what we see in either picture. This we call this a lattice structure, that these guys are weaved together in such a pattern that no one sodium is touching one other sodium. It always has a chlorine in between. And no one chlorine is touching any other chlorines. There's always the sodium in between. However, we can always simplify this to the discrete formula unit of sodium chloride. There's always one sodium for every one chloride. And so they don't always adopt a simple packing, but they will adopt some sort of repeating crystal structure that will isolate the cations from other cations. There'll be more talk about this in the second semester. The bottom left picture is a space filling model where it's all packed in really tightly. But the one on the right is one we usually use when we try to picture this, because it allows us to see all the interactions. That you can see, if I draw it from this center chlorine, it is adjacent to 6 sodiums. If I look at this centro sodium, it's adjacent to 6 chlorines, and that's always going to be the case. Now, the reason we don't see the other guys on the edges is because we have shortened the pattern just to fit it in the picture. But just know this pattern would continue up, down, front, back, left, right for millions and trillions of times. So, needless to say, each sodium is surrounded by 6 chlorines, and each chlorine is surrounded by 6 sodiums. However, not all of them will be ionic bonds. In fact, this chapter focuses mainly on covalent bonds. When we have covalent bonds, we are sharing electrons in order to make a molecule. Our Lewis theory teaches us that atoms will gain, lose, or share electrons until they achieve the noble gas configuration. Now, this is due to if you want to know why the noble gas, this is due to the high energy difference between each principal quantum number of the valence shell. So, filling all the electrons, once this is full, the next level is way up here. So to promote the next electron in is a big, big energy investment. If you said, I can invest $1 and I get $10 return in like 5 years, okay, that's good. If I say I have to invest $1,000 to get $1,010 in return in 5 years, that's a bit of an investment for very little return. Same way, filling that principal quantum number costs a little bit of energy, but we get a high return. Emptying it out the same way. Once we've emptied it out to a full S&P orbitals, the next loss is too high of an investment, so we don't get much of a return. This is called the octet rule. This whole filling out the s and the p orbitals. Octet. 2s, 6 from in the p, they add up to 8. Remember, there's only one s orbital, but it can hold 2. Only 3p, but each p can hold 2. Now, there's one major exception to this, and that's going to be hydrogen. Hydrogen, because it's in group 1, only has a 1s orbital. It will only need 2 electrons ever. So we call that the duet rule. It only ever needs a second electron. We should not be trying to add more electrons to hydrogen than its 2. Once we got that, we can stop. Now, there are weird exceptions. We are not playing with the majority of the exceptions. We're not going to worry about the majority of the exceptions. We're going to try to obey the octet and duet rule whenever possible. So how do we imagine covalent bonds? Well, when we have covalent bonds, got to remember the electrons are probabilistically found within a cloud location. And this has to do with the attraction of the nucleus between the electrons. Well, as 2 atoms approach each other, the electron cloud of one atom begins to become attracted to the nucleus of the second atom, and vice versa. So the electron cloud starts to distort so that the electron can get some of the beneficial, attractive benefits of getting close to the new nucleus. Now, eventually the atoms get close enough that the clouds have now fully overlapped. So it's allowing the electron within one cloud to be found within the same probabilistic region of the cloud of the second atom. Now, that's not to say that the electrons of atom 1 now belong to atom 2, but they're being shared. If you break that bond, typically the electrons, if you cleave it homolytically, the electrons go back to their original homes. But there's ways to cleave it in a way that the electrons stick with one of the stronger atoms. But the fact of the matter is those electrons are shared, and they're mostly still belong to the original atoms. Now, those electrons have to be obviously opposite spin so that they don't repel each other, and they're still found largely around their parent atom. But there's now an increased concentration region between the two atoms. So they now spend a lot of time between the two atoms as opposed to on the borders. And of course, we can get too close. If you kept making the atoms closer and closer, eventually the nuclei of each atom would repel each other again. And so that would destabilize this effect. But essentially there's a magical distance where the electrons are getting the highest benefit from being in the middle and without all the negatives of nuclear repulsion. But this is how we imagine a covalent bond existing. So we are going to represent these guys with Lewis structures. Now, a Lewis structure is just a simple diagrammatic representation that shows all of our compounds and their valence electrons. This is key. Valence electrons. We do not care about the inner shell electrons. We only care about the valence electrons. And these electrons will either be distributed via covalent bonds or in what we call a non-bonding lone pair. When we do a non-bonding lone pair, we will put a pair of dots. The lone pair, it's a pair, so there's two of them, but we call it a lone pair because they do not interact with anything else other than the fact that they're paired up. So this pair is not going to interact with any of the other pairs. Now, these are non-bonding, so they're not involved in further reaction. They're just hanging out there. These Lewis structures could contain as many as 3 covalent bonds between atoms, as a single bond, a double bond, or a triple bond. There is other exceptions to this, but we're not going to be able to deal with them with what we're dealing with. So single bonds, double bonds, and triple bonds. Each bond represent the sharing of 2 electron pairs. So a triple bond shares a total of 3 from one atom with 3 from another for a total of 6 electrons. And the important thing is that in the Lewis structure that all the s and the p electrons are accounted for. We need to count all of them and make sure they're all present. If you leave some out, you are not making a valid Lewis structure. And one thing to note is for most atoms, except for hydrogen and a few odd exceptions, most atoms will have 4 things coming off of them. A lone pair counts as one thing. Every single bond counts as one thing. So, looking at these compounds, we have HCl, hydrogen chloride. Hydrogen shares 1 electron with chlorine's 7 electrons. So hydrogen, because it has those 2 in the bond, gets its 2. Chlorine has 7, but it's sharing 1 with hydrogen, so it gets 8. As we see, there's 3 lone pairs and 1 single bond to give it 8. Oxygen, each oxygen has 6 electrons. So each oxygen is sharing 2 electrons with its mate to give it 8. So we have 2 lone pairs on each oxygen plus a double bond. 4 plus 4 makes 8. And nitrogen, with its 5 valence electrons, shares 3 with its mate. 3 plus 3 is 6, plus another 2 is 8. Each nitrogen has 8. All of these guys are stable structures. It's a stable Lewis structure. Now, due to the octet rule, there is a very strong inverse correlation between the number of valence electrons and the number of bonds an atom will make. Basically, the more electrons it has, the less it needs, and thus the fewer bonds it will make. Oxygen has 6 valence electrons. It only needs 2 more, so it only makes 2 bonds. Nitrogen has 5 valence electrons. It needs 3 more. It likes to make 3 bonds. Carbon only has 4, so it will typically make 4 bonds. And fluorine has 7, so it only makes 1 bond. Many pure elements, when they exist in their weird state, work based on that. Phosphorus, which exists as P4, exists as a triangle, essentially a pyramid, where each phosphorus is bound to 3 other phosphoruses so that it gets 8. Remember, nitrogen is in group 5 along with phosphorus in group 5, so it needs 3 to give it 8. Sulfur, when it exists as S8, forms this octagon shape crown structure where each sulfur is bound to 2 other sulfurs. Sulfur is in group 6, just like oxygen, and so it gets 2 more to give it 8. And the reason why they're not just binding with each other has to do with the size differentials. P and S are generally larger than N and O, and so they have trouble getting only 2 atoms close to each other, as opposed to the kind of more spread out, wider angle that you can get from these structures. Now, with that in mind, we're going to jump straight into organic compounds. Organic compounds are completely different from the Lewis structures we'll learn in the next video. What makes an organic compound? An organic compound contains a chain of hydrocarbons, mostly carbon and hydrogen, and they're held together in a series of covalent bonds, chaining carbon to carbon to carbon to other stuff to carbons. Now, in the Lewis structures we'll see in the next video, there is typically going to be 1 central atom. But in these guys, there may be more than 1 central atom. And so the way to figure out the possible Lewis structures is ways that use the formula as a hint. If I just gave you the formula for acetic acid is HC2H3O2, or even just C2H4O2, you could draw it several possible ways and not know which one is right, which one I'm asking for. However, as we're going to see in the following video, in the following slide, is if you can break these segments down into non-hydrogen atoms. You can break down a segment where carbon must connect to other carbon. We're going to be able to figure out how these work. We're going to break this compound down into individual segments, knowing that carbon will typically contain 4 bonds. Unless that carbon is on the end, well, actually, even if it's on the end, that carbon will typically need one of those 4 bonds to be bonded with something else. So that next segment. So we must always continue the chain. So we're going to draw a carbon with 4 lines coming off of it. and one of those 4 lines must be connected to the next chain. And then we'll fill in the rest of those lines with atoms that are adjacent to it in the formula. We're going to do the same thing with oxygens and nitrogens. Those are the 2 most common heteroatoms, atoms that are different from the carbon and hydrogen, that are going to be present in an organic compound. So, the only difference is that oxygen will only need 2 bonds. It will have 2 lone pairs, based on what we just saw. Nitrogen will only need 3 bonds. It will already have 1 lone pair. And hydrogen will only ever want to make 1 bond. Hydrogen will only ever be a terminal segment in these compounds. So, I will draw these guys out, the basic formula, and then we will show you what I'm talking about. How would we go about doing this? And I might even throw some new ones in here that aren't on here. Then give me a second to copy these down. CH2, Cl, and HSCN. Okay, with that in mind, let's go to the .cam. Okay, there we go. Okay, so my first step is everywhere a new carbon starts, or a new nitrogen or a new oxygen starts, I'm going to put a backslash through this to differentiate center atoms. So the hydrogens, I'm going to ignore the hydrogens right now. And so I got carbon, I got 1 atom, 2 atom, 3 atoms, 3 segments. So I got to draw these out. Carbon, carbon, nitrogen. All of these guys need to be connected. So let's start by just doing that. Carbon likes to have 4 bonds. So let's put 3 other dashes around this. Carbon likes to have 4 bonds. It has 1, 2. 2 other dashes. And nitrogen, here's the big thing. Nitrogen, with its 5 valence electrons, likes to have 3 bonds and 1 lone pair. So right here, now what are going to be fill in these places? Every single line should be accounted for. Well, this guy has 3 H's. So let's put H, H, H. Okay. This guy has 2 H's. Well, H, H. And the nitrogen has 2 H's. H. This structure is done. CH3, CH2, and H2. Structure's done. How about this guy? We have now this one's special in that it has an oxygen in parentheses, and we'll see why. If I draw this, I'm going to start by drawing it in a row, just like this. C, C, O, O. Each O wants to make 2 bonds and have 2 lone pairs. Each carbon likes to have 4 bonds. Okay. So if I draw it like this, we run into a direct problem. So H, we have 3 hydrogens left, and that goes here. Our problem is, what about these guys, these lines. So this structure is wrong. We don't have enough atoms to fill that up. And in this case, it's because that oxygen is not connected to this oxygen. If that was, it would look like this, COOH. But instead, we put the parentheses around that. So what other way could there be connected? If this was instead in between, let's move that over to here. So let's call that 3 and 3 prime. See, let's draw that same structure again. C, C. But now we have an O, lone pair. O. Okay. We still have a problem, but it's a slightly different problem now. This one has a line here and a line here unaccounted for. Line here and a line here unaccounted for. And that's because this is one electron that this guy has not paired up, and this guy's one electron that's not paired up. So what do we do with these single missing electrons? Well, I'm going to do the simplest thing, which is I'm going to take this electron and double them up. And now what do we see? See, carbon has 1, 2, 3, 4. This carbon has 1, 2, 3, 4. This oxygen has 1, 2, and 2 lone pairs. This oxygen has 1, 2, and 2 lone pairs. And so in this case, this is a structure that is more stable. Whenever you have two adjacent atoms with a bond unaccounted for on each atom, you can double them up to form a double bond or a triple bond if you have two sets of electrons missing. Let's look at the next guy. This guy is a little bit more back to basics. Break that up, break that up, break that up. So 1, 2, 3, 4. So carbon, oxygen, carbon, chlorine. Well, carbon wants to have 4 bonds. Oxygen only wants to have 2 bonds. Carbon wants to have 4 bonds. And chlorine, with its 7 valence electrons, much like fluorine, only wants to have 1 bond. We have 3 hydrogens right there. We can easily put them right there. We have 2 hydrogens right here. We're going to put them right here. There is our Lewis structure. Could I have exchanged the positions for the hydrogens and chlorines? Yes. These guys are absolutely reversible and you get the same answer. However, this guy is not the same answer. Cl H OH. This is not. We've changed around how the bonding has gone. We've changed that around. Or I could have put the chlorine there and swapped it with a hydrogen. Yes, but all these things are different structures and would be written differently in here. This one. So we'll just go ahead and go last guy. Split, split. So 1, 2, 3. So S, C, N. S likes to have 2 bonds because it's like oxygen. Carbon likes to have 4 bonds, and nitrogen likes to have 3 bonds and a lone pair. So what do? I erase one of these, and I double up. Okay? I erase one of these and one of these, and I triple up. Now suddenly carbon has 1, 2, 3, 4. Nitrogen has 1, 2, 3 in a lone pair. Sulfur has 1, 2, and 2 lone pairs. And you can do this for any organic compound that's linear in nature. I'm going to make up one fresh just off the top of my head. So let's see. What do we do if we have something like this? Okay, well, let's break this down. What does this mean? I can start my numbering from either side. I can call that 1, 2, 3, or I can call that 1, 2, 3. For the sake of this, I'm going to say 1, 2, 3. So what does this guy mean? That 2 right there tells us that there we have doubled up on our CH3. So there's a 3 and a 3 prime. So let's start drawing this in reverse. So we can go 1, there's our H. There's a C, there, let's put an H. Carbon likes to make 4 bonds. And we have C, there's a CH3. Here's another CH3. There's 3 and 3 prime. There's 2 CH3s bound to that center C. Let's do one more something else challenging. CH2. Another example of this. So something should be somewhat simple. 1, 2, 3. Let's see if we can figure this out. Carbon, carbon, carbon. Each carbon wants to make 4 bonds. Okay. 3. Put that in. 1, 2, 3. 1, 2, 1, 2. Not all of the carbons have all their bonds accounted for. So we're missing one here and one here. What do I say? We got to erase that. Double it up. So we have a CH3, CH double bonded to a CH2. That's what we have, because now we have 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 4 bonds all around. And that is a simplistic method of determining an organic structure. Remembering these rules, that they're only typically going to have 4 bonds on carbon, 3 on nitrogen, 2 on oxygen. This is always going to hold true for a neutral compound. The only way to break this rule is to make the compound charged. But we're not worrying about that right now. So, okay, that's where I'm going to stop. Have a good day.